Welcome to the second lecture of power quality. This lecture is in continuation with the previous presentation on the overview of power quality. So here we will talk about the effect of the harmonics on the power system. There are many negative effects or other consequences of the power system harmonics. Some of them are mentioned here. The one is about the neutral conductor overheating. The size of neutral conductors becomes more when there are harmonics. We can see in the next slide. The effect on transformer and machines, they get more overheated and they have more losses. Then the overstressing of power factor correcting devices such as capacitors, they also become threat to the power system when there are harmonics. Skin effect, that is high frequency effect on the power conductors. The losses in the motor. At harmonics, the eddy currents and harmonics create more losses in the system. And effect on meters. As you know, the meters are used to give the read about the energy consumed by the customers. If it is not properly designed to take care of the harmonics and unbalance, this may give erroneous readings. Okay. I will take some of them one by one. See the neutral conductor overheating. For example, if you have data centers where there are a lot of computers are being used, and you know that in computers we use SMPS, okay, kind of a converter which converts AC into different values of the DC, and they create third harmonic, fifth harmonic, seventh harmonic, and so on and so on, and most commonly these triplet harmonics. So the harmonics which have multiple of 3 times frequency of the fundamental. And these triple harmonics have interesting property. They rather getting cancelled, they get summed up because of 3 into 120 becomes 360, which is same as 0 degree. And they create the huge, you can say, magnitude in the current or voltage, mostly current here, okay, because the current is being summed up here, which becomes problem to the design of the conductor rating, neutral conductor rating. Sometimes the rating of this conductor goes as 240%, which is almost 3 times of the power conductor rating. Okay, this is very interesting. Normally the neutral should be of 0 size because it theoretically should not carry any current. But because of practical situations, the return current, which is sum of the 3-phase current, has to be carried by this. And sometimes this current is more than the phase conductor rating itself. Alright, this power factor is normally measured with the help of the some figure of merit they call the total harmonic distortion. TSD, most of you would have heard this name, TSD, okay, in your power electronic course. And TSD is defined as the ratio of harmonic content to the fundamental content. I will make the ink on so that I can make the comments here. So I will go to draw mode perhaps, and then it will be better, and take some pen here and then do this big size mode. Hope it will work. So this is basically IH, okay. This is the harmonic content of the current and divide by fundamental. So this equation comes out to be IH by I1. And what is IH? It is the RMS value of the harmonic content, which is nothing but I2 square plus I3 square and so on, plus IN square and square root. Similarly, you can see here that another figure of merit is basically I have to need to change color, I think, make it maybe red will be better to indicate the color. So go back. So this figure, later on we will prove that this value is equal to the power factor, which is PYS, in terms of the TSDs of voltage and current. You can see it here. Okay. So that we will prove later in the coming classes. And then another figure of merit is basically is the total demand distortion. This is nothing but equal to IHY I1. I. Okay. So difference is this term. It is I here, it is I1 here. Therefore, TSD or TDD, this is not TSD, this is TDD, please correct it. Okay. This is TDD. Therefore, TDD can never be more than 100% because it is the ratio IH by I1. I. While as this could be greater than, TSD could be greater than 100% depending upon the content of harmonics. It could be greater than 100%. Okay. While this is always less than or equal to 100% in case there is no harmonics. Clear? Okay. And how do we control these harmonics? There are two important methods. One is called tuned LC filters and the second is called active power filters. Tuned LC filters, you might be knowing this kind of a filter which you also use for the analog circuits, but this is for power circuit. Therefore, the current and voltage rating is quite high as compared to the analog filters. But concept is same, that you have to trap the harmonic component for which the filter is designed. The problem with the tuned filter is that you have to use number of filters for each frequency to be trapped. Hence, the problem of bulkiness arises in these applications. Active power filter are the modern solutions for filtering the harmonics, and as the name indicates, they consist of active power devices, mostly the power electronic switches. And the building block of the active power filters are therefore power converters, voltage source inverter, current source inverter. Okay, so these converters form the heart of the active power filters. And these are generalized filters which are adaptive in nature and compensates the load dynamically. You need not to have the separate filter for each frequency because it is adaptive and generalized in nature, so it can address, if it is proper rating, it can compensate all the harmonics alone. Now, apart from this, there are other terms like interharmonics, if you would have heard in your discussions earlier, or subharmonics. They are different from fundamental and the harmonics. Interharmonics are not integer multiples of the frequency at which the supply system is designed. Rather, they are fractional values of the fundamental frequency. It could be 1.2, 1.5 or 2.7 or even less than 1, that is 0.7 or 0.5. So these are being referred as interharmonics. If the frequency is below the fundamentals, they are called as subharmonics, like 1 hertz, 2 hertz. Okay, so these interharmonics fortunately are very less in power system and we never bother them because they are not significant in magnitude. However, they sometimes are caused by the cycloconverters, mostly induction motors and arcing devices if they are not properly functioning, and they mostly can be observed by a visual flicker. If it is significant in magnitude, you can see them as a visual flicker in display devices such as a CRTs, etc. Then another criteria for the waveform distortion was notching, if you remember. So notching is kind of a presence of notches in the voltage or current waveforms. Mostly the notches appear in the voltage waveform because of the sudden change in currents on the load side. For example, if you have a rectifier circuit, so you can see the rectifier circuit switches 6 times over a cycle in 3-phase system, and these 6 times are being reflected here actually. If you see, this is 1, this is 2, 3, 4, 5, 6. Again 1, 2, 3, 4, 5, 6. So each notch represents the switching operation of the converter. Okay, so this is called notching, and this may also become problem to the power system operation, because the zero crossing detection and the control circuit, the protection circuit, depend upon the smooth voltage waveform sensing. So if these are notches, sometimes zero crossing detection becomes the problem. Noise, as you know, is unwanted electrical signals with broadband spectral content lower than 200 kHz superimposed upon the power system voltage or current in phase conductors. These are mostly caused by power electronic devices, control circuits, arcing equipment, loads with solid state rectifiers, and switching power supplies. And these are normally mitigated by using the filters, isolation transformers, and line conditioners. Next important classification of power quality problem was the voltage fluctuations. As you know, the voltage fluctuations normally occur in case of heavy load variations. For example, if you see arc furnaces or electric builders, these kind of applications ask sudden change in the current over a period of time, and this causes uneven drop across the feeder, and hence the voltage fluctuates, not only in magnitude but also in frequency. Sometimes frequency is less than because of the certain converters used for that. Let us say cyclo converters, they use different frequencies, and these frequencies reflect back into the system modulations. Like this is, you see, fundamental frequency is there, but then there is a frequency of modulation here. Okay, or even the basic frequency is itself is 20 Hz, suppose, for example. So there could be two kind of things, one fundamental overlapped by 25 more oscillations, or 25 itself. Anyway, they are caused by large rapidly fluctuating loads such as arc furnaces and electric builders. They may not be very harmful to electronic equipment, but it is a more of a nuisance because it causes annoying, noticeable changes in the lighting levels. So when you read or when you do some work, you feel annoyed because it is changing in magnitude and frequency. Power frequency variation. Power frequency is another a fundamental parameter of the power system to monitor its health. So normally the power system frequency around should be fundamental frequency 50 or 60 Hz. However, it varies depending upon the power mismatch or power balance between the demand and the load of the active and reactive powers. Okay. Now, what happens when the frequency is varying out of the limits that is being prescribed by some standards? Then we need to act upon it through the governor action. So by, again, governor action is nothing but it matches the real power requirements to maintain the frequency. Okay. So this is another important aspect in power system. Now, knowing this, there is another dimension of power quality. This is called power quality monitoring. Now, as you know, the monitoring basically means that we will monitor what is the health of our plant and what are its various power quality parameters. It normally involves these important 4 steps. The one is data acquisition here, as you can see, okay, data acquisition here, and then second is characterization, and then power quality analysis and statistical analysis. So at each stage there are some functions. For example, at data acquisition stage we get all the parameters through proper transducers or sensors of voltage and current to their digital signals. And then there is a characterization. Based on these values, we characterize these parameters in terms of the RMS values, peak values, frequency, and so on, using various signal processing algorithms. And third is analysis part. Once these parameters are available, their characteristics of these parameters is available, then we can go for analysis, and also we do the statistical analysis, offline analysis. The trends of the PQ quantities like voltage and current variations, THD variations, these are being analyzed in a statistical manner, and the PQ indices are computed. Okay. This is a very general structure of PQ monitoring system. You can see here there is a place here where we put all the PQ meters. So they basically 1 to n, they measure all the important parameters, voltage and currents and so on. These are being passed over to the PQ analyzer, where we do analyze all these quantities, and then through LAN they are being stored into the client PC. Okay, a data storage kind of a thing, which can be shared with the whole system of things, the client PC, and through web server the other can access this information to take decision on the health of the power plant or any industry. And what are these parameters which are being read through this monitoring system? You can see it here. This stage we have a raw data. Okay, so you can see here that we have a raw data here. This is raw data here, and then we have the measurement characterization in terms of the half cycle RMS or full cycle RMS, and then we have characterization of event detection in terms of the sag, swell, and interruption, and so on, transient, harmonics, under frequency, over frequency, and so on. And finally, there is a data recording where all information is being stored here, and which is also used to transmit this information to the personal operators of the system. Okay. Now, what are the important quantities which are really monitored to indicate the health of the plant? In case of sag, swell, and interruptions, we are more worried about the duration, the magnitude. We are more concerned about the duration and the magnitude. Okay. The starting time, the clearing time, mean, and other values. And then there are you can say under voltage conditions we have similar parameters like duration, magnitude, starting time, clearing time, and mean value. In case of an unbalance, we have duration, unbalance factor, starting time, clearing time, mean value. In case of flicker, we have parameters duration, IFL, Ph.D, PLT, short term flicker parameters, long term flicker parameter, starting time, clearing time, mean value. In transient, there is a MA, BSA or happen time index. For harmonics, we have duration, TSD and TDD, starting time, clearing time. For under and over voltage, there are duration and frequency, starting time and clearing time, frequency variations. They are more explained here, the correct meaning. So these are the important parameters that I mentioned, okay? Sexual interruptions, under voltage, unbalance, flicker, transient, harmonics, over and under frequency. So as I mentioned, mostly we will be measuring the magnitude and duration, then starting time and the clearing time, okay? Starting time and the clearing time and mean value of these. In case of flicker, this is called IFL and Ph.D and PLT. They are special indices for measurement of flicker, and there is a starting time and clearing time mean value for this, okay? For transient, this is called mean absolute variation in squared amplitude, MAVSA. It is a special figure of index to measure the transient. It's called mean absolute variation in squared amplitude. Okay, now these particularly these parameters for flicker, they are called instantaneous flicker level, IFL, if you could see it here. Okay, they are known as instantaneous flicker level. This is IFL, and this is called as post duration. This is called the S for short and L for long. So this is long term flicker level measurement. This is the short term flicker level measurement. Okay. All right. And apart from that, there are other indices that can be looked into this for measurement, like TSD, as I said. As you know, TSD is one of them. Power factor is another parameter. Telephone interference factor is called the summation of the squared values of weighted squared values of the current or voltage divided by IRMS, square root of that. Then C message index is similar to this, except there are difference in the this one, weighting of the current or voltage. IIT product is the square root of the square sum of the square of WI square, IA square. So this is like a weighted RMS values. There are some equivalent indices to have idea about the effect of these quantities in when we weight them through certain values like WI. So this is similar to the current, except now we are using voltage. Then K factor for transformer is nothing but the ratio of WI square, IH square, and summation of them is square root by IH square. Crest factor, unbalance factor I discussed earlier, and flicker factor, so and so on. There are many figure of merits to indicate the power quality. Nowadays they use wavelet to indicate the signature of voltage and currents, to indicate how the voltage and currents are and what is their health. Now once we have measurement of power quality parameters, different parameters, and we have analyzed them, then this data is being stored when each event happens, okay? And this analysis and interpretation are very important of the power quality aspect of the power system, and they are being displayed or given to the personal operators sitting in the control room of the industry or plant, and there they can take decision, okay, by turning on and off the correcting devices, the circuit breakers, the relays, and so on. As far as the analysis and diagnosis is concerned, many methods are used for this purpose. Mostly artificial intelligence is more useful tool. And many techniques involve these methods, for example, fuzzy logic, artificial neural network, genetic algorithms, expert system, Bayes theory, and so on. Okay, I am not going into details of them. Those who are interested can study them through different papers or books. Okay, but this is another dimension of the work which we are not going to explore. We are mostly focusing on the fundamental aspects of the power quality. Because this is an overview, so I thought I will give you a more broad spectrum of this course. Now you might be thinking that who will decide what should be the limit of harmonic content, what should be the limit of voltage variations, what must be the limits of the frequency variations, etc., etc. So for that, from the beginning, IEEE, called Institute of Electrical and Electronic Engineers, has been quite active, and they developed certain standards for these quantities, power system quantities. So IEEE and IET, which is managed by UK, okay, and IEEE is managed by USA. The headquarters is in USA. These two are the leading agencies which invite the experts all over the world to set the standards. Some of the standards are being mentioned here in context of the power quality. You can go through them. For example, IEEE 1159 is very common for monitoring the electric power quality. Then it has a various sections, 0.1, 0.2, 0.3. They talk about the power quality characterization, the file format, and power quality data, and so on. IEEE P 1564 talks about voltage sag indices and so on. So you can go through them, okay? And when you have free time, you just have an idea that what kind of standards are used to characterize which kind of performance. For example, IEEE 1547 is concerned about the distributed resources and electric power system interconnection. Apart from that, there is the IEC, it's called International Electrotechnical Commission. Its head office in the Geneva, Switzerland. It was founded in June 1906, London, UK. So IEC is another agency which sets the standard for the operation of the power system. For power quality, we have these important standards: IEC standard 61000, which deals with the requirement of monitoring and measuring the harmonics. IEC standard 6100415 describes the instrumentation and the procedure for the monitoring the flicker and so on. Okay. Then it has various parts like 430 and 28. They talk about the overall recommendations for monitoring the all types of power quality phenomena, and IEC standard 6100028 describes about the unbarment, the voltage dips, and short interruptions. Okay. In India, we have three important agencies. One is called CEA, Central Electricity Authority of India, and CERC, Central Electricity Regulatory Commission, and SERC, State Electricity Regulatory Commissions. These work in coordination to follow these standards. To once they once they take some standards, IEEE standard or IEC, because mostly technology comes from these places. So most of the time we are landed in we have landed in following these standards, actually IEEE standards. So CE basically handles the construction of electrical plants, electrical lines and connectivity to the grid, installation and operation of meters, the grid standards and safety. CERC looks into a power sector in India, and it is a statutory body functioning with quasi-judicial status under section so and so. The State Electricity Regulatory Commission basically concerns on state grid code, state supply code, standard of performance of the distribution licenses. Now this is mostly the same as the center code, because state cannot operate at different grid code. So almost every state has to go through the standards and follow the functioning of their power plants in synchronization with the others. I will give you just brief idea about that what it means to follow the standards. Mostly voltage and frequency are the first two important parameters that have to be followed in a certain limits. For example, if you see IEEE, then IEC, then CA. Okay, so they are in close match. In fact, they are almost same. Like voltage allowed is basically minus 10% downside and plus 6%, while IE says minus 10 to plus 10%, and CE says minus 10 to plus 10. This is Central Electricity Authority of India. And frequency variations are normally plus minus 5 Hertz. We will analyze some of the standards here and see how they are being interpreted or how they are being considered for the power system. For example, if we say IEEE 519, okay, then it says that based on the voltage level of the distribution system, these are the permitted harmonics level in the system. For example, if you say 120 volt to 69 kilovolt, the permitted harmonics are given in this table. So there are two parameters. First is the voltage level. Second thing is the ISC by IL. What is ISC by IL? This is the ratio of short circuit current to rated current or load current. And this shows basically the short circuit capacity of the bus. Okay. The higher the value of this parameter, or short circuit ratio you can say, SCR. So higher the value of short circuit ratio of the bus, the more sturdy it is. So this is less than 20, then 20 to 50, then 50 to 100, and then 100 to 1000 and so on. So as you can see that as we increase the short circuit ratio of the bus or short circuit capacity of the bus, then it has a more tolerance for the harmonics. So allowable TD is 5, 8, 12, 15, 20. So higher capacity bus can withstand more harmonic. This is the interpretation of this. And another important thing is that, read that even harmonics, okay, even harmonics are limited to 25% of the odd harmonics. You may ask, well, this is odd harmonics, what about even harmonics? These are limited to 25% of the odd harmonics. And current distortion that result in a DC offset, such as a half-wave converters, are not allowed. So DC component is not allowed at all. Since most of the time we have a symmetric operation of the load in terms of the waveform, so they are hardly present DC offset. Okay, and this is in favor of the healthy power system, that we should not have any DC offset. So this is about the voltage level from 120 to 69 kilovolts. What happens if the voltage is more, let us say 69 to 161 kilovolt? Okay, then for this voltage, for more higher voltage, but for the increasing order of the short circuit ratio, you can see the pattern is same, that TD is increasing. However, at higher voltage, the relative values are less than the previous ones. Okay, the rest are same. When you go for more than 161 kilovolt, they are further less. Okay, they are further less. They are using here THD. Sometimes they are using TDD, THD. Okay, depending upon the context. Maybe they are more worried about the fundamental ratio as compared to the THD. But in nutshell, they indicate the same kind of behavior. So you see that when the voltage goes up and up, the permitted values of harmonics are less and less. And for increasing value of short circuit ratio of the bus, the allowable THDR can be allowed slightly more than those are having less SCR. Okay, I hope you understand this pattern. So this was about the current aspect, and if you go for voltage distortion, I think this is about mostly about the current one, and this is for the voltage one. Okay, so for the voltage one, if you see that if the 69 and below is allowable, THD is 5%, for 69 to 161 2.5, and for 161 it is 1.5. So this is also indicating that if you increase the voltage, the allowable harmonics are less as compared to the less voltages. And then the second part of this, the final presentation of this overview talks about the voltage acceptability tolerance curve. Okay, we know that any device has some maximum or minimum voltage limits for which it can operate faithfully. If the voltage is very high, it may likely to be damaged. If the voltage is very less, it may not even switch on. Okay, so this kind of a behavior are basically called as voltage acceptability tolerance curve. And there are many agencies, associations who have been working for this, like CBMA is called Computer and Business Equipment Manufacturers Association in 1970. Then ITIC was given new name for the CBMA 96 called the Information Technology Industry Council. Then SEMI 47, Semiconductor Equipment and Materials International. IEEE P1346 talks about displaying the SAC data for equipment compatibility. And IEC, International Electrotechnical Commission, they talk about this curve called voltage acceptability curve. What is this curve? It actually shows that what is the levels of voltage that can be tolerated by a machine or by a electrical equipment over a period of time. Okay, so if you see it here, you can see this region. Okay, this region, I'll make it green region, is the acceptability region. Let us say computer, for example, you want to operate a computer. So this is the voltage which can easily be accepted for computer. For example, the voltage is here 250% above the rated value. So 0 means here the voltage is same as the rated value, and 250 means the 250 above the set value. If the voltage is not within this range, then it is called over voltage, and if voltage is not this range, this is called under voltage. Okay? Clear? A very interesting point is that you may think that if the time is very small, such as let us say 0.0001 second, okay, which basically means then 10 microsecond. This is 100 microsecond. Then this is the 1 second here. So depending upon that, you can accept very large voltage from here to here for a small time. It basically means that even if you have, let us say, 1000 volts applied for a computer for a short while of 1 microsecond or 10 microsecond, then nothing will happen to computer. Nothing will happen to computer. And even if the voltage is minus 10, minus 100% down, means completely it is 0 voltage. Even then, nothing will happen to computer. You would have seen if there is a power off for very small time, those good computers will not turn off, even they are not connected to the battery, or you can say UPC, uninterrupted power supplies, UPS. So even if the power is not there for very small time, and even if the voltage is very high, the computer operation will not be affected. However, if this goes for a longer time, for example, same voltage is here, okay, if voltage is here, then it will be affected because time is more. And B into time becomes a kind of a some figure of index, that voltage for how long time? A small voltage, how long time? High voltage, how long time? And this limit is the steady state limit. You can see it here. So once we have plus minus 10% variations here, then it can operate infinitely on continuous operation basis. So this is the meaning of voltage acceptability curve. Basically, it talks about the impact of the energy on the device. Okay, so B into T becomes kind of energy. B square T, if you look at here, B square by R is kind of energy, and power, and into T means becomes energy. So it's a basically energy graph, energy acceptability graph for a device. Okay, so I will stop here, and this is the second lecture to discuss about the overview of the power quality. In the next class, I will talk about the applications of power electronics to the power system. So this will be also extension of the presentation. So maybe 1 or 2 more presentations, and then I will come to more abstract discussion on the blackboard or whiteboard to explain the concept from single phase systems. I will stop here. So I will see you in the next class.